In part 1, we started our investigation of the decimal representation of fractions by looking at some unit fractions. We saw that for the first few, they fell into two categories: terminating decimals, like 1/2, 1/4, and 1/5, and periodic decimals, like 1/3, 1/6, and 1/7. A couple of questions occurred to us. First of all, were these the only two categories? And we answered that in the first part. We said, yes, it is. There's nothing else that can happen other than these two. And we also asked ourselves, is there a way that we can determine what type it's going to be without having to go through the work of actually working it out? We saw that if we have a unit fraction and its decimal is terminating, then the denominator has to have only 2 or 5 as its prime factors. Not only that, if we have the prime factorization of the denominator, we could tell how long that representation is going to be, how many digits are going to make up it, as well as what the digits actually are. And the digits will either be related to powers of 2 and 5. In part 1, we started with fractions and looked at the patterns in the decimal representations. In this part, we're going to do that in reverse. We're going to start with the decimal representation, how to turn that into a fraction, and look for patterns there. So we got to think about how to turn decimals into fractions. So when we went from fractions to decimals, we just did long division. If we want to go the other way around, it depends on what type we're looking at. If it's terminating, that's pretty easy. We can just use the definition of our place value system. So for example, if we have 0.321, that really means 3/10, 2 100ths, 1 1,000th, and then we can just find a common denominator of 1,000 to get 321 over 1,000. And now we can actually do that quicker. We can look at 0.321. We see that 321 is going to be the numerator. The denominator will be 1 followed by 3 zeros. Now what would happen if we actually started with 0.33333, 0.3 repeated, which we know is 1/3? How could we look at that thing and end up with a fraction? So let's work backwards. So if we let x be this 0.333 repeated, one thing we'll notice is since this thing is periodic, if I do 10x, I get 3.333. We're now, after the decimal, we have exactly the same thing going on here as with our original number, which means that if we subtract our original number from 10x, we're going to get rid of the decimal part. And I'll just be left with 3 over here, 9x, which means I can solve for x. X is 3/9, which reduces to 1/3. Okay, so this seems like a valid method for attacking these. Let's look at one that's a little bit more interesting to see if we can find a pattern. So if we start with 0.52 repeated, then I need to multiply it by 100 to get it so that we have exactly the same part after the decimal as our original. Subtract our original. We end up with 99x equals 52, which means that x equals 52/99. Now I'm starting to see a pattern form here. Let's go one further and just to see if it keeps working. So if I've got something like 0.703, so 3 decimals in the period, I multiply it by 1,000 to get the decimal parts the same as the original. Subtract the original. 999x equals 703. So x equals 703 over 999. So it seems we do have a pattern here. We saw that if I've got 0.3 where 3 is repeated, I had 3 over 9. If I had 0.52 where the 0.52 is repeated, I got 52 over 99. 0.703, 703 is repeated, I get 703 over 999. If our pattern actually continued, that would mean if I had something like 0.1234 where the 1234 is repeated, I should have 1234 over 9999. If I had 0.12345, I should have 12,345 or 99,999. And if I had 1, 2, 3, 4, 5, 6, I should have 123,456 over 999,999. And in general, if I have a repeating decimal that's made up of n digits that are repeating, my fraction is just going to be those decimals that repeat over the number 99999 that has the same number of digits as the repeating part. So this seems to be what our pattern was. So let's take a look at an example. Now keep in mind that these things also may reduce. So we can see what the thing's going to be, but we might have to reduce it afterwards. So let's look at an example and show that our pattern works. So if we took this 0.1234 repeated, which we're assuming to be 1,234 over 9,999, I want to compare that to 1,234 over 10,000, which is just 0.1234 with no repeating. So if I take the difference between those two things and find a common denominator and do a little bit of algebra, I've got a common 1,234 in each case, so I can take that out. And I can write this in the form 1/10,000th times 1,234 over 9,999. Now, if I take this expression and rearrange it, since I'm really interested in the decimal representation of 1,234 over 999, I can write it as 1,234 over 10,000, so that's 0.1234 plus some extra stuff. What's the extra stuff? Well, it's just 1/10,000th of our original fraction. Now, it might not make much sense to have this fraction defined in terms of itself, but if we're a little bit sneaky about it and a little bit thinking on our feet, we can sort of plug this definition, this whole equation, right back into itself. I can replace this 1,234 over 9,999 with this whole expression. And if I simplify that, I now get 1,234 over 10,000 plus 1,234 over 10,000 squared, which is 0.1234, 1,234 plus some other stuff, which again is in terms of the original. And if I continue that process, I'm just going to get 1,234 over 10,000 plus 1,234 over 10,000 squared plus 1,234 over 10,000 cubed, and so on. And if I write that as a decimal, that is our 0.1234 repeated. Based on the pattern that we saw, we're going to take a little detour and we're going to talk about the rep digit numbers and the rep unit numbers. So a rep digit number is just a number made up entirely of a single digit. So things like 55, 7,777, and 88,888,888,888. These are all rep digit numbers. Now a subclass of that is the rep unit numbers, which are rep digit numbers that only use the digit 1. So we're going to use the notation R sub n to represent the rep unit number made up of n ones. So a couple examples. R2 has 2 ones, R5 has 5 ones, and so on. And these are going to become important because we saw the denominators in our fractions for periodic decimals turned out to be that 9999, which is a rep digit number, which we can actually write as 9 times a rep unit number. And we're going to be interested in looking at some features of the rep unit numbers to tell us about some repeating decimals. So one thing that's going to happen is if we have a number that's a factor of this 9999, and it's not a factor of a smaller number of the same type, then 1 over that number is going to be periodic, and the length of the period is going to be n, the number of nines. And the period, the digits that are going to be involved, is just going to be this 9999 divided by that number, and possibly padded with some zeros if that's a number that's smaller than n digits long. So let's look at a couple examples. So for example, 7 is a factor of 999,999. If I divide 999,000 by 7, I get 142,857. If I start with 1/7, multiply the numerator and denominator by 142,857, I end up with a fraction 142,857 over 999,999, which by our pattern we know is the periodic decimal 0.142857 repeated. Similarly, 37 is a factor of 999, and if we go through and do the division, we get 1/37 is 0.027 repeated, and 11,111,111 is a factor of 99,999,999. Dividing that, we can write 1 over 11,111,111 as 0.00000009 repeated. Next, we're going to use a result from high school algebra to help us out. In grade 10, students see the factorization of a difference of squares. X squared minus y squared equals x minus y times x plus y. Later on, they're going to discover that this is actually the first in a large infinite family of identities of the same type. If we're trying to factor the difference of 2 powers that have the same power, the difference of the 2 terms is always going to be a factor. And we can use this to our advantage. And not only that, if we look at the second term, there's a pattern in that, so we can kind of predict the 2 factors. So for the problem that we're considering of looking at the decimal representation of unit fractions, we're really interested in, for repeating decimals or periodic decimals, the factors of this rep digit number that's a bunch of 9s repeated. Now, that's just 10 to the 10 to the n minus 1, but 1 is a power of 1 for any power. So I can really consider 10 to the n minus 1 as 10 to the n minus 1 to the n. And I can use my identity. I know that 10 minus 1 is going to be a factor, and using the pattern in the identity, I can write out the other factor, do a little simplification, and I end up with 9 times the rep unit digit, the rep unit number of n digits long. Which isn't particularly helpful because we could have looked at this and said it's 9 times 11111. However, if we're a little bit sneaky about things and we're a little bit creative with our thinking, we can actually deal with some situations and use this to our advantage. So for example, if n is a composite number, then we can use some power laws, use the fact that 10 to the 6 is actually 10 squared cubed, a fact that we see in grade 9, and rewrite this 10 to the 6 minus 1 as 10 squared cubed minus 1 cubed. And now we can use the identity dealing with cubes instead of 6 powers. And if we do that, run through the pattern, we get 99 times 100 squared times 100 plus 100 plus 1, or 9 times 11 times 10101. If we rewrote it as 10 cubed squared and went through the same process, we get 9 times 111 times 1001. So an interesting thing happens. For one thing, these two expressions are representing the same number. So as a result, we can actually look at the various factors and learn a little bit about the prime factorization. I know that 11 is a prime, so 11 actually has to go into one of these. If I do some division, I can break things down and I can go back and forth. So I can actually get at the prime factorization of this 10 to the 6 minus 1. And hopefully you're starting to see a pattern. If we go and consider something bigger, like 10 to the 12th minus 1, which consists of 12 nines, since 12 is 2 times 6, I can write this as 99, or 9 times 11, times 101010101. Now, if we look a little closer at that, it looks like I've got these blocks of 01. So I've got an 01, an 01, an 01, an 01, an 01, except for the beginning. But really, if I stick a 0 in front of that, it doesn't change the number. It's just our convention that when we've got numbers, we don't have to write down leading zeros because they don't really tell us anything. They don't change the number. They don't affect the number at all. So if I look at this 10 to the 12 minus 1 is the rep unit number made up of 2 ones multiplied by something that's a bunch of blocks that are size 2. And how many blocks? 1, 2, 3, 4, 5, 6. 2 times 6 is 12. If we go a little further, 12 is 3 times 4. I'm going to get R3 times something that's made up of 4 blocks that are 3 long. 4 times 3, I get R4 times something that's 3 blocks that are 4 long. 6 times 2, I get R6 times 2 blocks that are 6 long. And in some cases, we can actually keep going. So if we look at this one where we've got 10 to the 12 minus 1 is 9 times R6 times this 2 blocks that are 6 long, since I've got R6 here, I already know something about how this thing factors. I can write that as a block R2 times 3 blocks of 2, or I can write it as R3 times 2 blocks of 3. But now these are actually the same number. And as a result, these two things have to be the same, like we mentioned earlier. So if we look at that, if I look at 11 and 111, they don't share any prime factors, which means that since these are the same numbers, any factors of one has to be factors of the other, which means 11 has to be a factor of 1001. And similarly, 111 is going to have to be a factor of this 10,101. And if we just do division, we get 91 times 111 is this 10,001. 91 times 11 is this 1,001. And if we use the fact that we can easily factor 111 into 3 times 37 and factor 91 into 7 times 13, we can put that back into our original expression and get this, an almost prime factorization of that 10 to the 12 minus 1. And if you think of trying to do the prime factorization of that 12-digit number by hand, that's going to be a little bit rough. Whereas here we've used some properties of the Repunit numbers to help us out. Now, if we actually go back and look at some of those other forms of the 10 to the 12 minus 1 and compare just like we did here, we can actually eke out the last two prime factors and get this factorization of this guy. So if we look at this prime factorization of 10 to the 12 minus 1, we know that if we have any factor of that number, then the reciprocal of that number, that factor, is going to have a period of length 12. So for example, if we look at 1/11, which is a factor, it's 0.09, which has a period of length 2. And when I said a period of length 12, that doesn't necessarily mean it's going to be the smallest period. If we have something of length 2, every 2 repeats, which means if I look at 6 blocks of this, 09, 09, 09, 09, 09, 09, that's of length 12. And if we kind of look at blocks of 12, that's going to repeat. We have to be careful of sort of when we're talking about period, whether we mean any period, or whether we're talking about the smallest period. So some other examples: 1/13 has a period of length 6, which goes into 12. 1/37 has a period of length 3, which goes into 12. 1/101 has a period of length 4, which goes into 12. And 1/9901 actually has smallest period of length 12. So what are some conclusions? If we consider this Repunit number that's n digits long, if d is going to be a factor of that, then its reciprocal is going to be periodic, where the length of the period is going to be a factor of this. If n is composite and a is a factor of n, then we know that Ra is a factor of Rn. So if something like 11 is a factor of 1111, as well as R6 and R8 and R10 and R12 and so on. And if we look at these B's, these block numbers that I'm calling them, if I have these blocks, like I said, A-1 blocks of length n over A, or I can think of it as A blocks of this if I consider the first block to be 0,0,0,0,0,1 as well. That's a factor of Rn when that thing is going to be composite as well. So in other words, B23 and B32 are both factors of R6. So if we find prime factors of Rp for prime values, and we find prime factors of these block type numbers, that will tell us about the periods of the reciprocals. So for example, if we look at the prime factorization of the first few Rp's for prime p, now the first one is prime, the second one we could have done by hand. The other ones, I've used Wolfram Alpha to factor these things into primes. Similarly, if we look at these block numbers, notice that I have no BN1, because if the block length was 1, it's just a Repunit number. And so we factor a bunch of these things. And remember that like B22 is going to go into R4, B23 is going to go into R6, and so on down the line. So what are some consequences of all this stuff? Well, For example, if we look through those two tables, we see that 7 is a factor of B23, which means that it's going to be a factor of R6, which means that it's going to be a factor of 10 to the 6 minus 1, which means that 1/7 should have a period of 6. Similarly, 37 is a factor of B32, which means that 37 is going to be a factor of R6. But if we look at the table for the RPs, we see it's also a factor of R3. So yeah, we can consider the reciprocal of 37 to have period 6, but that's not going to be the smallest period. It goes into R3, so it's going to have period 3. And similarly, since 7 is a factor of B23, which is 1001, that means that if I divide 1001 by 7, it's going to be an integer. Another way to look at that is 1000 divided by 7, or 1000/7 plus 1 divided by 7 has to be an integer. So what does that mean? Well, if I look at 1/7 as a decimal, it looks like that. If I look at 1000/7 as a decimal, I just move everything over 3 spaces. Similar to what we did when we looked at changing the repeating decimals into fractions. But in this case, the repeating parts don't match up. And not only that, we're not subtracting, we're adding. And when we add those, we get 142.9999999. And if you don't know so already, you can use the same sort of reasoning that we did when we changed repeating decimals into fractions to show that 0.99999 is actually the same as 1. So 142.99999 is actually going to be 143. Now, what does that mean? So if we take the period of 1/7 and break it into 2 pieces of length 3, those things add to 999. So 142 plus 857 is 999. Or if you look at it, digits that are 3 apart are going to add to 9. And this is actually how I memorize the decimal form of 1/7. I know that 1/7 starts 7, 14, 28, and then I remember this, so that once I've got the 1, 4, 2, 8, then the 1 and the 8 gives me the 9, the 4 and the 5 gives me a 9, and 2 and 7 gives me 9, gives me my last couple of digits. But an interesting thing is 7 is also a factor of B32, and if we go through exactly the same process, we'd see that blocks of 2 of the period are going to add up to 99. So for the reciprocal of 7, for 1/7, the period taken as blocks of 3 add up to 999. The period taken as blocks of 2, those 3 chunks add up to 99. Okay, for this next part, we're going to introduce modular arithmetic and sort of look at the problem from another point of view. So, Gauss gave us this notation. We read this as A is congruent to B mod C. And what that tells us is we use that notation when C is a factor of the difference between A and B. Or another way to think of that is that if A and B have the same remainder when we divide by C, they're congruent to each other modulo C. For example, if we look at 7 and 13, they're both odd, which means that if I divide them by 2, they leave a remainder of 1, which means that I can write 7 is congruent to 13 mod 2, and they're both congruent to 1 mod 2. Similarly, 55 and 2300 are both multiples of 5. They leave a remainder of 0 when we divide by 5, which means that we can write 55 is congruent to 2300, which is congruent to 0 mod 5. And finally, if I write 25 equals 3 times 7 plus 4, and 137 equals 19 times 7 plus 4. It means that if I divide 25 and 137 by 7, they both leave a remainder of 4, which means that 25, 137, and 4 are all congruent mod 4. Now, a useful way to picture sort of modular arithmetic when we're working a certain modulus is to line the numbers up like this. So if I'm looking modulo 3, if I write the numbers out 0, 1, 2, 3, 4, 5, 6, 7, 8, you'll notice that in the columns, in this column are all the multiples of 3, which are congruent to 0 mod 3. All these are 1 more than a multiple of 3, which are congruent to 1 mod 3. All these are 2 more than a multiple of 3. So a couple interesting things happen. If I look at 11, it's congruent to 2, sort of the highest number up on the list there. 7 is congruent to 1. And if I add 7 and 11, I get 18, which is congruent to 0. But if I add the things at the top of the column, 1 and 2, they add to 3, which is also congruent to 0. Which means that when I'm dealing with operations, with numbers in modular arithmetic, I can basically use anything in the same column. So usually we use what are called the reduced numbers, sort of the smallest numbers up here, so 0, 1, and 2. In some cases, we can actually get a little bit trickier and include negative numbers. So I could include in this, if I go to negative numbers, -1 would be in this column. If something's 2 above a multiple of 3, it's 1 below it, -2, and so on. But we won't need that for what we're doing here. Similarly, 4 and 1 are congruent, 5 and 2 are congruent. And if I multiply them, I get 20, which is congruent to 2. But if I multiply the things in the column 1 and 2, it's congruent to 2 as well. And what that means is, when we're dealing with our operations, addition, subtraction, multiplication, division's a little bit dicier, we won't get into that, we can deal with the reduced values. In number theory, we can actually create a new number system, which in actuality, we're naming our 3 numbers, these whole columns, these equivalence classes. And the operations that we're doing are actually on the equivalence classes, not necessarily on the particular numbers. But the numbers are called representatives of these classes, but we don't need to get into that. So for us, if we go back to the first lecture when we looked at showing that 1/7 was periodic, we did a long division. If we just zone in on part of that division, this part here, if I ignore the decimal, I can look at this as 1,000 divided by 7, and I'd see that that gives us 142 with a remainder of 6. From which I can conclude that 1,000 is going to be congruent to 6 mod 7. They have the same remainder. Is there an easier way than going through this division? Well, I know that 10 is congruent to 3 mod 7, which means that 100, which is 10 squared, is going to be 10 times 10, which is equivalent to 3 times 3, which is 9, which is equivalent to 2 mod 7. So 1,000, which is 10 cubed, is going to be 10 squared times 10, which is going to be equivalent to 2 times 3, or 6 mod 7. So we could get at this value much quicker by using modular arithmetic. And if we look at the powers of 10 mod 7, look what happens. Anything to the 0 is 1. 10 to the 1 mod 7 is equivalent to 3. 10 2 is going to be 3 times 3, which is 9. subtract the 7 is equivalent to 2, remainder of 2. 10 to the 3 is going to be 10 times this, or 3 times this, which is 3 times 2 is 6. 10 to the 4 is going to be 3 times 6 is 18, and 18 is 14 plus 4. The next one is going to be 3 times 4 is 12, which is 7 plus 5. The next one is going to be 3 times 5, which is 15, which is 14 plus 1. And now we're back to here, which means that this whole chunk here is just going to repeat. And if I keep going, I'm going to have this thing periodic, so that if I look at it, this thing is periodic with period 6. A very useful result in elementary number theory called Fermat's little theorem. You might have heard of Fermat's last theorem, very famous problem, but this is another result from Fermat. He showed that if p is a prime, then a to the p minus a is a multiple of p for any integer a, which if we put it in terms of congruence, it means a to the p is congruent to a mod p. Now if we back up and look over at our table here, my number was 10, which is 3. If I go 3 to the 7 is congruent to 3, just like Fermat said. Now, if a is not divisible by p, then we can actually sort of divide this through. If a was divisible by p, well, then that means that a is congruent to 0, and 0 to anything is equal to 0. But if it's not divisible by p, then a to the p minus 1 is going to be a multiple of p, which I can write as a to the p minus 1 is congruent to 1 mod p. And again, if we go back to our table, there's my p7. If I go to the power of 6, there's my 1. So for our purposes, if we're dealing with prime numbers other than 2 and 5, because 2 and 5 go into 10 and this would fall apart for that, the power of 10 mod p is going to eventually hit 1 by the Fermat's little theorem. And as a result, it's going to repeat and be periodic. And that tells us that the decimal representation of 1 over p is going to be periodic. So since 10 to the p minus 1 is congruent to 1 mod p, we're going to have a cycle that's going to end after p minus 1 terms, which means the period of the decimal representation is going to be a divisor of p minus 1. It might be p minus 1, or it might be something that goes into it, just like we saw before. So here's some examples. If we look at 1/3, its period length is 1, but 3 minus 1 is 2. The most it could have been is 2, but it was 1. For 1/7, the biggest it could have been was 6, and it actually is 6. For 11th, it could have been as long as 10, but it was actually 2 that goes into that. So you see some will be divisors of this number, and some will actually be that number itself. In number theory, we call the order of a particular element modulo n, as long as they don't have any column and factor, the smallest exponent that we have to raise that number to give us 1. And if that order is as large as possible, then that number m is called a primitive root modulo n. And again, for us, if 10 is a primitive root modulo some prime, then the decimal representation is going to be as big as possible, that p minus 1. So here are some examples of some primes where 10 is a primitive root. The smallest one is 7. That has a period of length 6. Next is 17. 1/17 has a period of length 16. 1/19 has a period of length 18. 1/23 has a period of length 22. and 1/29th has a period of length 28. Now, it isn't an easy problem to figure out whether 10 is a primitive root or not mod p. That's sort of something, if you want to study number theory, you'll come up with some techniques to do that, but there's not like an absolute way to determine that. But it just gives you an idea of how that result is related to our problem. So for our last part, let's put it all together. Up to this point, we've been looking at some various results to determine the period of, in most cases, reciprocals of primes. But what if we want to consider fractions whose denominator isn't a prime number? So in terms of periodic fractions, there's a couple of types. We can have the purely periodic fractions. This is my term. This isn't a known term. If a denominator can be factored into primes such that none of the primes are 2 and 5, and the highest exponent of any prime is 1, then 1 over d is going to be periodic with period p, where p is the least common multiple of the periods associated with the primes. And by purely periodic, I mean right after the decimal, the period starts and away you go. So let's look at a couple examples. So 1/7 has a period of 6. 1/11 has a period of 2. The lowest common multiple of 6 and 2 is 6. So that means if I look at 7 times 11, 1/77 is going to have a period of 6. And if we work it out, there it is. 1/77 does have a period of 6. Similarly, the periods of 1/3, 1/13, and 1/41 are 1, 6, and 5. The lowest common multiple of 1, 6, and 5 is 30. So the period of 1 over 50 and 99, which is 3 times 13 times 41, is going to be 30. And if we actually work that out, that's indeed what happens. So a couple interesting things that we can see. These thirds, because the period length of 1/3 is 1, it means that if we sort of multiply a prime by 3, it's not going to affect the length of the period. It's going to be exactly the same. Now again, my term for mixed periodic fractions means that the fraction is going to, the decimal representation is going to be periodic. Eventually, we're going to get a couple of digits that aren't part of the period, and then the repeating part starts. So when does that happen? So if the denominator can factor into primes such that 2 and or 5 are factors of d, and the highest exponent of a prime other than 2 and 5 is 1, and we have some other prime other than 2 and 5 in there, then the decimal representation of 1 over d is going to start with a non-periodic part whose length is determined by the exponents of 2 and 5. So from the first video, if I look at the 2 and 5 part, it's going to determine the length of the chunk at the beginning, and the periodic part's going to depend on the primes other than 2 and 5. Now, this highest exponent of 1 is there because if we know that 1/7 has a length 6, to go to 7 squared or 7 cubed or 7 to the 4th, there's not an easy way to determine the length of those things. In some cases, going up by powers will just multiply by the same thing. So I think for 7 squared, 1 over 49 has a length of 6 times 7, which is 42. But that doesn't always happen. And again, that's sort of a more difficult problem in number theory than we will get into. So let's look at some examples. So 120 is 2 cubed times 3 times 5. So if we look at the 2's and 5's, we have 2 cubed times 5. From that, we know that the non-periodic has length 3 because this is going to go into 10 to the 3. If I look at the periodic part, which is going to depend on 3, it's going to have length 1 because the length of the period of 1/3 is 1. So this tells us that we should start with 3 digits that aren't going to be part of the repeating pattern, and then one number that will repeat. And if we work it out, we get 1/20th is 0.008, that non-repeating part, and then the 3 is the part that repeats. Similarly, if we look at 22,550, it's 2 times 5 squared times 11 times 41. Again, looking at the 2's and 5's, the highest exponent is 2, which means that the period is going to be, the non-periodic part is going to be of length 2, because those things go into 100. And if we look at the non-2's and 5's, the length of the period of 11 is 2, the length of the period of 41 is 5. So this is going to be of length 10. And if we work this out, we're going to get 2 digits that we start with that are not part of the period, followed by 10 digits that repeat. Now, we can find out what these digits are going to be, but now it's going to become a little bit more work involved in that. We could predict what the repeating digits were going to be for 1/11th. We could repeat what the digits were going to be for 1/41st. We could predict what the digits would be if it was just 1/2 times 5 squared. But once we start combining those things are all going to multiply together, and it becomes uglier. You can still do it, but that would be another 20 minutes, and I don't think anybody's interested in listening to me ramble on for 20 more minutes. And anybody that would be interested in that could probably go and work it out for themselves. So that's it. That's all for this. I hope that you've enjoyed our look at fractions. In the future, I'm going to do a few more of these. I'm going to try to bounce around between different topics, do some geometry stuff, do some more number theory stuff, do some probability, so that we get sort of a wide variety of topics. And hopefully the next one will be a little bit shorter than this. My first one, I might have got a little bit carried away, so hopefully we'll make it a little bit more appropriate next time.